Hey everyone, we will now be presenting our NSF Engineering Research Center presentation, which is about thin film and dopant engineering for future electronics. My name is Shashank.
I'm Mohammed Farouk.
And I'm Brendan Duffy.
Before diving into the details, I'd like to start by giving a quick overview of today's presentation. We'll begin with a brief introduction where I'll outline the motivation behind this research and the broader context that frames our work. Then we will move on to the scientific justification, explaining the fundamental principles and the key challenges that make this research significant from both theoretical and practical standpoints. Next, we will present our research thrust proposal, highlighting the core objectives, methodologies, and the unique approaches we plan to explore, particularly focusing on doping engineering as illustrated on the right. After that, we will discuss applications and system relevance, where we will show how our proposed work connects to real-world technologies such as logic devices, transistors, photodetectors, and memory systems, all of which rely on precise doping strategies to optimize performance. Finally, we will conclude with our roadmap and collaboration plan, detailing the projected milestones, timelines, and potential partnerships that will drive this research forward. Altogether, this roadmap provides a complete picture from the scientific basis to system-level applications of how doping engineering can serve as a foundational element in next-generation electronic and optoelectronic devices. Modern electronics are increasingly reaching fundamental limits in both thin film deposition and dopant engineering. As device dimensions continue to shrink, achieving precise control at the atomic scale becomes extremely difficult. We face scaling challenges, not just in terms of atomic precision, but also in maintaining energy efficiency, material sustainability, and device reliability. These factors critically affect overall performance and manufacturability. Current fabrication techniques such as chemical vapor deposition, ion implantation, and high-temperature annealing are well established, but they come with trade-offs. They often lead to dopant diffusion, interface defects, and high energy consumption. These limitations become especially restrictive when we look at next-generation technologies, including quantum, neuromorphic, and flexible electronics, which demand higher precision and lower processing temperatures. Our research goal is to develop novel thin film and dopant engineering methods that can achieve atomic level precision while operating at low thermal budgets. To do this, we're focusing on several key areas: dopant defect interactions, low temperature process design, and the use of sustainable materials to support scalable, eco-friendly fabrication. Finally, this effort will be highly interdisciplinary, integrating expertise from materials science, electrical engineering, and computational modeling. Together, these collaborations aim to drive energy-efficient fabrication and strengthen U.S. semiconductor competitiveness on a global scale.
So we're trying to do an analysis for ion implantation being a cornerstone for how doping works. And the main issue that make ion implantation very important is because it's the main thing we use to make doping in our semiconductors. And one of the biggest problems that we face, or kind of several problems that we face with ion implantation, is that it's not that much or not that much precise for the kind of application that we want to have 5 or 10 years ago, as we gonna 5 or 10 years coming, as we're gonna see in the roadmap. And at the same time, it can actually cause degraded mobility because of the way that those kind of bombarding ions at the wafer can cause defects in the lattice, as well as some metal impurities or contamination at the surface of the wafer that could also affect doping process, which can result in non-uniformity in the performance of different dyes on the wafer, as long as also there's thermal stress, which can cause some diffusion in the dopants, and this can actually lead to something like RDF, which would overall decrease the performance of our devices. Such things and challenges significantly actually damages our devices. Simplest of what we can say is the MOSFETs MOSFETs actually can face very harsh variation in their threshold voltage, leakage currents, and power efficiency. When you have a lot of ion implantation not going specifically as you want, also sensors can face mismatch when they are processing data. And AI chips definitely also will face a lot of problems with the devices or the transistors are not functioning properly. So our approach to solve this problem, or at least provide some kind of a framework for solving it, is deterministic ion implantation. Instead of just trying to shine a beam of ions and make some kind of a bombardment at specific parts of the wafer, you're actually targeting a single ion to hit a very specific part of the wafer and then see how that collision happened, or like see the end results of that collision, which is a feedback system that you get feedback its results and you compare it with what you desired in the first place, and upon that you could actually do some kind of an arithmetic approach to how much of bombardment you need at specific parts to achieve lower than 1 nanometer scaling of that ion implantation, and therefore very precise doping. You would require things that can make very focused ion beams, as well as a high ability of detection so that you can make the feedback system work properly. But the overall result of such a thing is that we're going to be more closer to having ideal devices, or devices with ideal channels, like a MOSFET with an ideal channel, at which the random dopant fluctuation will be so minimized because you will have a very precise doping that will help you to sustain the device characterizations and increase the reliability, the overall reliability. So if we can achieve those kind of things, there will actually be a lot of applications that will be very, very benefitized by this new solutions that we have proposed. So the first of them is AI hardware, because AI hardware is all about very high performing and very low. If you actually can make systems that can consume less power at high computing energy, which is what our approach of ion implantation does, then this is very useful for AI hardware, as well as neuromorphic chips, because neuromorphic chips are actually trying to imitate the human brain and a 3D volumetric architecture. So if you can do very precise ion implantation, that helps you actually to carve, or like to shape this 3D volumetric shapes that is required for those kind of chips. Uh, for quantum devices as well, there is research going that deterministic ion implantation can actually help in generating more stable quantum bits, which is very useful for quantum devices, and definitely in MEMS, because if you have more stable, or if you have better and higher precision ion implantation, you will be able to have better sensors, and therefore your MEMS devices will be much more efficient. So overall, this kind of approach is actually very beneficial for a lot of applications with wide variety of usefulness.
Right, so we've identified a lot of really interesting use cases for this device, but manufacturing it and making sure that it's a feasible, marketable product, that demands a pretty comprehensive roadmap. So what we've laid out is a 4-phase, 10-year roadmap that details the conceptualization and then iterative improvements to the design. A first phase is mainly procuring all of the hardware necessary for this ion implantation, and then also detection machine. So first, for like the focus ion beam application, we'll look at pre-existing solutions or attempts at solutions for the single ion implantation methodology. There's a company out there called Ionoptica that proffers a single ion beam technology, but they claim a resolution of about 5 to 10 nanometers, which is roughly an order of magnitude more than what we want. So we would combine this then with beam optics that we select from select companies. And then, of course, as we mentioned before, the detectors that will be responsible for engaging in that closed loop control to make sure that we can gauge exactly how many ions are being implanted. And then other systems as necessary will be procured to conduct the annealing necessary, and then also to establish an ultra high vacuum. And to complement the hardware that we're looking at, we'll also be investing significantly in software at this portion, specifically with TCAD simulations to simulate the ion events and to compare an ideal case, as we mentioned before, with what might actually be realizable by our device. And then we could also leverage code that looks at multi-million particle analysis, just to look at the long scale throughput of the device. And then maybe we could leverage deep learning as well for predictions on the device's overall reliability and statistics for output. Then in phase two, which is going to be about as long as phase one in length, we'll revise some of the software and maybe even implement a multi-physics analysis regime in COMSOL or ANSYS to look at more of these systems level effects, because we are combining a few different pieces of semiconductor equipment. So that would be necessary. And then we would likely begin actual experimentation where we would look at an array of sites that each require an ion implantation. And then we would try to aim to implant about 10 to 100 ions with about 10 nanometer spacing to get within about an order of magnitude of our final requirements for the end of the product life cycle. And what we'd look for is the efficiency of the detector in detecting the total dosage, sputtering latency, which is how quickly the ion beam could get cut off through that closed loop control, and then also positional accuracy of the stage and any moving components for the wafer. Our second two phases are each 2 years. The first one is mainly about refining that experiment I talked about just a second ago, and then also adapting it for many of our future use cases. So instead of just an array of sites that we'd be implanting ions on, we would look at possible future technologies like a primitive neuromorphic array, or we would look at a conventional AI hardware application like a tensor processing unit. And then we would use the material qualities of that and the geometry in our simulations and experimentations to find the necessary parameters for the device itself. And then we would also conduct some experiments on the thermal annealing, specifically with samples that have undergone advanced packaging processes or use the different materials commonly seen in advanced packaging technology so that we can ensure an appropriate temperature is being applied. And then, of course, we would wrap everything up with a throughput study to ensure that all processes happen at a maximum speed and that any bottlenecks could be eliminated. And then lastly, in phase four, that's when we would begin to finalize the prototype and then roll it out to any university application, industry application, or even a national lab that would be interested. And this can also be accompanied by workforce development programs that work with the NSF and National Science and Research Foundation. And then we could also leverage CHIPS, the CHIPS Act and the Science Act for funding. And then that could be used to either onboard new employees or fund university programs related to the research. And that really takes me to some of the broader impacts of the design itself. There's four main impacts beyond just creating a successful deterministic ion implantation device that really should be considered. The first is that with CHIPS Act funding, there's a lot of opportunities for university partnerships for students at the undergrad or graduate level who are interested in getting involved with the design. There's so many different components to it, so a lot of different ways for students in various disciplines to get interested. On a more professional level, at the national laboratory level, cross collaborations could be made with like Idaho National Laboratory or Sandia National Laboratories, just comparing the different equipment used that could not only accelerate the development of our device, but also help them in their research. At an industry level, disseminating this product to industry would really ramp up the production of the next generation technologies we're talking about, like the neuromorphic arrays or the stable quantum dots. And then lastly, on a non-technical level, this opens up a lot of opportunities for students to learn more about semiconductors, maybe a student who's never considered the industry or doesn't consider themselves an engineer could take a look at this through some kind of media application and gain an interest for the device. And in that way, you could really nationalize and popularize this kind of semiconductor technology. And that brings us to the end of our presentation. Thank you very much.